Hmm? Hello, everyone. Good morning there in the United States. For those who are attending from the United States, good evening here in the Philippines. I am Jet Aguilar from the Astronomical League of the Philippines, and I will be your host for today's webinar. Thank you so much for joining us for our second Astronomical League of the Philippines Astronomy Expert Speaker Series, which also coincides with our celebration of the 2022 Global Astronomy Month. I'm happy to see a lot of registrants attending not only from the Philippines, but from other countries as well, like the United States, United Kingdom, Italy, and Germany, to name a few. Last week, we had a great talk given to us by Dr. Jay Pasakov on the topic observations of the December 4, 2021 total solar eclipse from Antarctica. Today, we are very fortunate to have another great talk and great speaker whom we will be introducing to you shortly. Before we start the program, kindly allow me to explain some rules for this webinar to help us make this an enjoyable learning experience for everyone. Kindly listen to the lecturer and refrain from making any unnecessary distractions. There will be a short question and answer session at the end of the lecture. You may type in your questions under the Q&A tab found in your Zoom interface at any point during the presentation. We will do our best to answer questions live or via the Q&A tab. We would like to remind everyone that the contents presented in this webinar will remain as the individual property of the lecturer and the photographers in the presentation. We will also be distributing certificates of attendance via email to all registered attendees who will be present with us throughout the webinar tonight or this morning. So please use the name you have written in your registration forms to help us facilitate this process. Enjoy the webinar and have fun learning. Here is the program for the webinar, with our esteemed speaker presenting his talk on visualizing Hubble's colorful universe. After the talk, we will also be showing a short 7-minute video presentation on the highlights of Philippine astronomy and the Astronomical League of the Philippines. Let me turn you over now to our president, Mr. James Kevin T., for his welcome remarks.
Good evening, everyone. The Astronomical League of the Philippines is happy to welcome everyone to its second Astronomy Experts Speaker Series 2022 webinar in the celebration of National Astronomy Month. Global Astronomy Month, which is organized every April by the Astronomers Without Borders, which is the world's largest annual global celebration of astronomy. Each GAM, which brings new ideas and new opportunities. And the GAM 2022 this year is no exception. Once again, bring enthusiasts together worldwide to celebrate Astronomers Without Borders motto, One People, One Sky. So for tonight, we would like to welcome Mr. Zolt Levay, who will be giving us a very interesting lecture entitled Visualizing Hubble Colorful Universe. To cut it short, Zolt Levay is a retired principal science visual developer in the Office of the Public Outreach at Space Telescope Science Institute in Baltimore, Maryland, USA. We are fortunate to have also another two more eminent distinguished astronomers experts who will be speaking via this Zoom webinar on their particular field of interest for the next few weekends. So aside from Zolt, we also have upcoming Joe Rayo, who will be sharing his lecture on a night of shooting stars, which will happen on May 7th, so 8:13 Philippine time. And The next one is Mr. Eclipse himself, the Fred Espana, who will also be giving us a lecture on predicting and chasing solar eclipses on May 29, 2022, 10 p.m. So to get the ball rolling, I would like to turn over to Ms. Imelda Hozon, who will welcome our guest speaker for tonight.
Thanks, James and Jet. Welcome, Zolt. Ever since Galileo Galilei first took a peek through his telescope, humanity has strived to build bigger and better telescopes. It is every astronomer's dream to be able to use the best and most powerful telescope out there. Today, we are so fortunate to have as our guest speaker an astronomer and photographer extraordinaire who uses the Hubble Space Telescope to produce some of the most impressive and stunning images of the universe. I came to know Zolt Levay back in the late 1990s while I was photo editor at Sky and Telescope magazine. When the magazine needed the latest images from Hubble, Zolt was my go-to person. Oftentimes, he's still working on the images I'm requesting. And when he sends them to me, he never failed to always remind me that the files were still under embargo. It was truly a privilege and an honor for me to be one of the few people who gets to see some of Zolt's work before it's even released to the public. And they never fail to impress me. Zolt became interested in astronomy and photography at an early age. He started reading Sky and Telescope while he was in high school. He earned his bachelor's degree in astrophysics at Indiana University, Bloomington, and received his master's degree in astronomy at Case Western Reserve University in Cleveland, Ohio. He worked on several space science missions at NASA's Goddard Space Flight Center in Maryland before joining the Space Telescope Science Institute in 1983. As principal science visuals developer in the Office of Public Outreach at STSci, Zolt produced images and other visuals from data provided by the HST to publicize science results from Hubble and other observatories. He also led the Hubble Heritage Team, whose work showcased the finest images from the Hubble Space Telescope. Friends, it is my great honor to welcome today's speaker, Zolt Levay.
Thank you. Thank you, Imelda. Thank you, everyone. Thanks to all the organizers. And it's a great honor to be invited to speak here tonight for you, this morning for me. Thanks to technology, we can do these things remotely. It's kind of amazing, isn't it? So I'll get started here, share my screen, get all the technical stuff out of the way. So tonight I'd like to talk about my experiences working with data from the Hubble Space Telescope. And as Imelda said, producing some of these spectacular images. It's been my great privilege to have this opportunity to work with some of the best astronomy data that's available. And as I like to point out, it's not my work really that makes the images so spectacular. It's really the quality of the telescope and the fact that it's above the atmosphere. I'll get into that a little bit more. So I'd like to start out by reviewing a little bit about Hubble itself. Of course, it's a astronomical telescope that's orbiting the Earth. So it's above the atmosphere and above all the distorting and absorbing that the atmosphere does. I mean, we all like to look up at the night sky and see the stars twinkle, and it's very nice and romantic, but it's a real pain for astronomers. So astronomers have been trying to build telescopes on higher and higher mountains because you get above more and more of the atmosphere that distorting and absorbing atmosphere. But ultimately, even on the highest mountains, you still have to look through the air. So finally, a few decades ago, we were able to put a telescope in orbit. And it's not the first astronomical telescope in orbit, but it's the largest and most complete astronomical observatory. And so the other part of the name is it's the Hubble Space Telescope. So the space part is obvious, it's in space. The other part of the name Hubble comes from this gentleman, Edwin Hubble, after whom the telescope is named. And Edwin Hubble was a very prominent astronomer in the American astronomer in the 20th century. He made fundamental discoveries and advancements about the nature of the universe. And so NASA felt, once the telescope was launched, that it deserved to be named after this gentleman, Edwin Hubble. So Hubble has been in orbit since 1990. That's now 32 years. It just passed its 32nd year in space. And that's actually a very, very long time for a space mission. Space is a very harsh environment. Things go wrong. And so, very few spacecraft last as long as Hubble has. One of the main reasons it's lasted so long is because of the ability to service it using NASA's space shuttle program. And astronauts have gone 5 times to the telescope and been able to replace parts of the telescope that have failed, put in new technology, new instruments, new cameras. As you're all aware, technology advances at an extremely rapid rate, and we have much, much better equipment now than we did in the 1970s and 80s when Hubble was being designed and built. So it's been very fortunate that Hubble has been able to keep up with that technology to some extent. Now we're limited now because the last servicing mission was in 2009. That's a long time ago now. Even that's a long time ago for a space mission. And we have no shuttle program anymore. So there's no real chance to service the telescope. But fortunately, it's been working and continues to work. I may point out this particular image that one of my favorite photographs from one of the servicing missions, the last servicing mission in 2009. Here, an astronaut has just removed the old workhorse camera called Wide Field Planetary Camera 2, and he's replaced it with the newer version of that instrument, the Wide Field Camera 3. So he's holding on to the old camera and getting ready to stow it in the shuttle's cargo bay and bring it back to Earth. If you happen to be in Washington, D.C., you can go to the Air and Space Museum and see this camera in the museum. It's kind of fun to see that. It took a lot of some of the most memorable and widely distributed pictures that you see from Hubble. And now this camera is the real workhorse imaging instrument. And it's the one that's producing a lot of the images now, along with several other instruments that are doing great science work. So what does Hubble do? Well, it's a general purpose observatory. So it looks at everything that astronomers want to look at, from our nearest neighbors in the universe, the solar system, the planets in the solar system. These are just a few of the objects that are in the solar system and that Hubble has looked at. These are, of course, the brightest planets that we can see: Mars on the left, Jupiter in the center, and Saturn at the upper right. Beautiful objects. And Hubble's not maybe the most optimal instrument to look at these things. We've now sent lots of missions to many of these planets, gotten very up close images, much, much more detailed and higher resolution than Hubble can provide. But Hubble does have one advantage in that it has this long-term observation capability, so that we've looked at these planets over now many decades. And we see weather patterns on Mars, for example. We see clouds on Mars, and we see the changing weather patterns. We see the ice caps change. We see changing cloud patterns on Jupiter and Saturn. So, these long-term kinds of things are one of the things that Hubble can do that other short-term space missions can't do so much. You might be curious, what's this black spot on the face of Jupiter? Well, there's a red spot on Jupiter called, imaginatively called the Great Red Spot, which is a big storm in Jupiter's atmosphere. But the black spot is the shadow of one of the larger moons of Jupiter. So we see these shadows cross Jupiter fairly frequently. It's kind of fun to see those. And you also see the satellites crossing across Saturn and their shadows on the cloud tops of Saturn. So farther out in the universe, we see all kinds of fantastic things out there. This is in our own galaxy, in the Milky Way galaxy. We live in this galaxy, this conglomeration of stars and gas and dust and planets and rocks and all that stuff. This is a bubble blown in the material between the stars by a very bright hot star that's emitting a lot of very intense radiation, light, and also material from its surface, and blowing through the material between the stars and forming this bubble. And then also compressing the gas in these other regions, and ultimately will form new stars out of this medium, this material between the stars. And another example of a place where there's lots of gas and dust. This is the one of the more iconic places that lots of people like to observe. It's called the Horsehead Nebula in the constellation of Orion, near one of the brightest stars in Orion's belt. And this is an unusual view of this object because it's in infrared light. So with the newest camera on Hubble, it has an infrared capability. So it can see near infrared light, which is able to penetrate a lot of the gas and dust that absorbs the visible light that we can see with our eyes. So this is all light that we cannot actually see, but Hubble is sensitive. Hubble's camera is sensitive to that light. And the interesting thing is that we can actually see things beyond this that are the infrared light. We see distant galaxies through this that we cannot see the visible light coming from those galaxies, but we can see the infrared light. And farther out in our galaxy, we see places like this, which is the remnants of a supernova, that a star that blew itself apart and emitted all its material from the star out into the space between the stars, and now is glowing because of the shock wave from the explosion of that star is passing through this medium and energizing it and causing it to glow in different colors of light. Now, the different colors come from different chemical elements that are producing light of different wavelengths, and therefore different colors we see as different colors. And I'll talk about that too a little bit later. So we see the whole cycle of stellar formation and destruction that happens in the universe. And farther out, much farther out, everything we've seen so far is in our own galaxy. Our galaxy looks something like this. This is another galaxy that we see far out in space. This is called the Sombrero Galaxy for its resemblance to a Mexican hat. This flat disk of stars and gas and dust, and this bright bulge of stars providing a glow across a more spherical glow that surrounds this flat disk. And we see evidence of the dust in this galaxy by the dark band along the edge that's absorbing the light from the bright stars behind it. This is a great example of the kinds of galaxies that we see. And again, we see much more distant galaxies in the background. Almost every Hubble image that we look at, we see these galaxies much, much farther away. And then we see groups of galaxies. They form small groups, larger groups, big clusters of galaxies. This is actually one of the newest images that's been released. This was produced and released to commemorate Hubble's 32nd anniversary, which happened just this past week. Actually, on the 24th of April is the date of the launch of the telescope and deployment of the telescope. So it's kind of fun to see new images coming out from the same camera. Everything's still working pretty well. And again, we see not only this wonderful cluster of galaxies, we see a combination of different types of galaxies, a more elliptical galaxy with less star formation going on, less dusty material. And then we see spiral galaxies here that do have more dust and are continuing to form stars out of that dust and gas. And we also see that they're somewhat disturbed, and they're not regular spirals like we all often see. And they're disturbed because they're in close proximity to other galaxies, and the gravitational forces of the interactions of those galaxies causes them to get distorted. And this is actually a pretty mild case. In other cases, the distortion is much, much greater. And then farther out, we see these massive clusters of galaxies. And there is so much mass here that this phenomenon of gravitational lensing takes place, where the gravity is causing the light that's coming from behind these galaxies to be distorted, just like an optical lens distorts the light. So mass bends light, as Einstein demonstrated many years ago. And it's proven, Einstein's ideas of this or demonstration of this is now proven very effectively by looking at objects like this, where we see all these very distorted features, and even distorted even more than the distortion that happens of galaxies that are interacting with each other. And this is purely an optical distortion. So regular looking galaxies behind this cluster, the light from them is being distorted by the mass, the matter in this cluster of galaxies. Most of the matter actually is unseen. It's dark matter, and yet it still interacts gravitationally. So it causes this gravitational distortion and this gravitational lensing, even though we can't see the light. There's no light being produced by this matter. It still has effect on the gravity. And in fact, if we study the distortion very carefully, we can kind of reverse engineer the distribution of matter in the galaxies and determine the density of that matter across this region of space, which is to me a very fascinating result from studying objects like this. So that's the kind of thing that Hubble has been able to do for us scientifically. And so just to concentrate a little bit more on some of the things that, some of these images, this is actually one of my favorite images. It's called the Karina Nebula. It's a very large region in our own galaxy, back to our galaxy, where it's a very dynamic region of space. There's a lot of material here. There's a lot of gas and dust that's interacting with itself and interacting with the stars. Lots of young stars. There's a cluster here of stars that formed not too long ago, maybe a few million years, which is not very long in cosmic timescales. It's obviously very long in human timescales, but not very long in cosmic timescales. And these stars are very young. The hottest stars are still very actively burning their nuclear fuel and producing huge amounts of energy and actually material that's coming off of those stars. And that material, we see the effects of that material in the other regions of gas and dust here. They're sculpting these regions into these pillars and compressing that material to the point where new stars are being formed, a second generation of stars is being formed deep within these pillars of gas and dust. And we can see the effects of that it's a little difficult to see at this scale, but we see jets of material coming from those newly formed stars. So that's a telltale signature of newly forming stars deep within. Even though we can't see those stars directly, we see the effects of them. So not only that, but we see older stars here that are actually reaching the end of their lifetime. They're burning their fuel so rapidly that they don't they don't last for very long. And one example of that is over here, this very bright star called Eta Carina, that's some people think is a good candidate for a supernova, for it to blow itself apart in a cataclysmic explosion sometime in the near future. We can only hope that it goes off within our lifetimes. It would be an amazing event to see a supernova that close within our own galaxy. It's a very rare event. So anyway, I think this picture is a perfect example of seeing the entire life cycle of stars just in one field, in one image. Now, it's a complex image. It was constructed from about 50 separate exposures from the Hubble Space Telescope, stitched together in a large panorama. But beyond that, it was also combined with data from a ground-based telescope, the Cerro Tololo Observatory in Chile, to provide the color information. So the brightness information came from all from Hubble data in the light emitted by the element hydrogen. And then color information was added from this ground-based data. So another example I like to show is this wonderful spiral galaxy. It has this classical spiral shape. It's actually called a barred spiral because it has this straight feature going through it, and then the wonderful elegant spiral arms coming off the ends of that bar. But this particular example I like because it has so much detail in it. And one of the details, some of the details that we can see are these dust structures that we see very clearly, of course, in the Hubble image, and also these regions of newly forming stars. These are exactly analogous to what we see in the previous image, where new stars are being formed, and the telltale color, this pinkish color, is coming from the light of hydrogen, which is the main constituent of the gas that we see in these regions. And then beyond that, we see lots of other details. We see very deep into the very bright center of this galaxy. And one of the features of Hubble's optics and sensors is that it has this immense dynamic range. That is, it can record a huge range of brightnesses, and we can still see details in the faintest parts of this image and in the brightest parts of the image. And with some processing that we'll see a little bit of an example later, we can preserve all that detail that's in the data. We can preserve that and see this amazing regular spiral structure that's deep within the core of that galaxy. And then beyond that, in the fainter parts of the image, another amazing thing about this image is, again, we see much more distant galaxies beyond this galaxy that we see in the mid ground of our field of view. So these galaxies are hundreds of times more distant than this nearer galaxy, which is named NGC 1300. and right through the disk of this galaxy, where there's a fairly large amount of material obscuring, but we still see those very distant galaxies through the disk of the galaxy, which is remarkable to me. So where do these images come from? Well, they come from data. They come from data taken by the Hubble Space Telescope, cameras in the Hubble Space Telescope. And as we see color, the cameras do not see color. They don't see color the same way we see color, where our eyes separate out color in the scene into basically three ranges of color, roughly red, green, and blue. And then our eyes send that signal to our brain, and brain kind of puts that back together as a color view of what we see. Hubble's cameras work pretty much the same way, but we have to have some manual intervention to reproduce that color. So the cameras include filters that restrict what colors the cameras will record. So astronomers want to study different aspects of the objects they're looking at, and those aspects can be determined by the color of the light that they're going to record. And that color is determined by the wavelength. So the different filters restrict different ranges of wavelengths of the light that are being recorded by the camera. The camera can record a wide range of wavelengths. In the case of the primary camera on the telescope, from the near ultraviolet to the near infrared, and all the visible light in between. The filters, again, restrict what range of colors the camera will record, whether it's a very narrow range or a broader range, more like what our eyes can see. So in a real world example, these are three images taken through three different colored filters, red, green, and blue. And you can see that, on first glance, they don't appear very different. If you look a little bit more carefully, you can see some differences in the images, but it's not real obvious. So what we do in software, once we have the images, we can apply color to those monochrome, to those black and white images. And then when we combine those images together, then we can see all those colors that are inherent in the data. And it's satisfying to see that when these images first get put together, that the colors are what you expect them to be, in the sense that, as I was describing before, these are galaxies. Again, this is a small group of galaxies, some of which are interacting with each other. And we see different features in these galaxies. We see blue areas that are regions of young hot stars that are preferentially blue. So lo and behold, in the images, they come out blue. There's more blue light than red light. So the blue is more prominent in the images. There's also red regions, again, either where there's predominantly hydrogen emission, which is red to our eyes, and we see that as red in the images. Other red regions are because there's predominantly cooler stars, which emit more red light than they do blue light. So they appear red either to our eyes or in these images. Or areas of dust where the blue light is scattered away and the red light comes through. So, so again, the colors are what we expect them to be. Now here's a different example, and these are taken with filters that restrict a very narrow range of light, of colors of light that match the types of light that are emitted by these areas of space, where it's the gas that's emitting the light. The gas is being energized by very energetic radiation from hot, bright stars that are actually not in this view, but are energizing the gas. And then the gas emits light in particular colors, and that color depends on the type of gas it is and the physical conditions of that, the temperature and the pressure and so forth. So in this particular area, the brightest emission, the predominant constituent of the gas is hydrogen. And that emits in red light. So there's a filter that matches the wavelength of that hydrogen emission. But there's also other elements, other gas in this area of space. Oxygen, for example, is fairly predominant, and it emits light in the blue, more in the blue or blue-green. And then there's also sulfur. These are the brightest emissions that happen in most of the time in regions of space like this. This particular image is maybe very familiar. It's called the Eagle Nebula. It was not this image, but an earlier version was taken shortly after the telescope was serviced the first time. And the new camera was put in. This was one of the very early images that was made. This particular version of the image is a later image that we took on the 25th anniversary of the telescope. So here again are three images, black and white images, as the camera sees them, but taken through the three different filters. And if we apply the colors to that again, we apply the primary colors, red, green, and blue. Now, you may be wondering why we're not using red for hydrogen, where that's the color that we would see of that light. We're assigning green to that because we're working with this model of color, red, green, and blue, the way our eyes see light and the way every color technology works, this three-color model. Your computer monitor, your television screen uses these three colors, these primary colors, red, green, and blue, to produce all the colors that we can see or that your device can produce. And so we're using, we're shifting the colors, we're kind of redefining the colors so that we're able to use all the colors that we can possibly use. So if we applied the color, the unfortunate thing is that the sulfur light is very similar in color to the hydrogen light. So in order to separate the hydrogen from the sulfur, we're putting those in the different colors. And the reason we're using green for the hydrogen is because the hydrogen is slightly shorter wavelength than the sulfur. It's a little more energetic. And so we're putting the reddest light, which is the lowest energy light, we're making that red. And the intermediate one we're making green, and the highest energy light, the oxygen light, we're putting into blue, which is much closer to the natural color of that. So again, if we put those together, we have an image that looks much like this. This is kind of the initial raw view of the image. It's been processed a little bit, but then, and then this is the kind of subjective part of this. There's a lot of objective parts of putting these images together, calibrating the data, a lot of which happens semi-automatically or through software in the data pipeline. But then other parts of producing these color images is much more subjective. So you have a lot of choices in how you render these images, the range of brightnesses that you choose, and how you scale the images into the visible part of the image that we're going to visualize. So with a little bit more processing, it's kind of a subtle difference, but we can add a bit more contrast, shift the color to be more pleasing and interesting, and make what I think of as the most dynamic, the most interesting image that we can. And as I believe Imelda alluded to in the introduction, these images were produced primarily to describe or to illustrate the discoveries from the telescope that we were announcing. And all the major discoveries from the telescope. We put out a press release, and the images accompanied those press releases to illustrate what the science was that the astronomers are trying to describe. And so in some cases, the images were designed to illustrate a particular aspect of that science, and so they were constructed in a way that emphasized that rather than making the most dramatic image or whatever. So, but the images, many of the images turned out to be pretty dramatic anyway, and it's a result of the data more than the processing really. So this is again some of the best astronomy data that's available, and so it wasn't the processing so much that made the images dramatic, but it was the content of the data. So I felt very privileged to be able to produce these images. So I wanted to shift gears a little bit, and I like to say that these images represent our best view of the universe, and that view of the universe it relates very directly to nature as we see it on the Earth in a very personal and human way. And we need special instrumentation to get these images, whereas with any camera that we have, we can see the great features of the Earth's landscape, but it's still nature, and it's a continuum of nature, whether we see it with our own eyes here on the Earth, or we see it with specialized instruments in the very distant universe. And it kind of struck me after a while that there's some very direct correspondences between the natural world that we see here on Earth and the natural universe that we see much farther out in space. And this is one example. So on the left is the image that we were just looking at, the image of the Eagle Nebula, these pillars of gas and dust in the Eagle Nebula. And on the right is a pillar of rock in a national park in Utah in the United States. It's a pretty well-known feature called Delicate Arch in Arches National Park. And visually, it has a lot of correspondence. The color is interestingly similar to the color that we see in the Eagle Nebula image with these reds and browns and yellows. And in fact, they were produced in kind of an analogous way. So on the rock, on the right, the rock has been eroded, the less dense rock has been eroded away, and its denser remaining rock is left over. The erosion took place by wind and water and so forth. On the left, there's no water involved necessarily, but there is wind. There's wind from stars, material that's actually eroding this gas. It's all gas and dust, so it's very tenuous compared to the rock on the Earth, but it's an erosion process. So I thought there was an interesting correspondence there. Another example is this on the left is a wonderful image of what's called a planetary nebula. This a star buried deep inside this region of gas and dust that's emitting its outer layers, sending its outer layers out into space, and then it's a very hot star, and causing this gas to emit light. And there's a disk of material way down close to the star that's constricting the flow of material off the star into these kind of cone-shaped regions of space. And so here on the right is a geyser in Yellowstone National Park in Wyoming in the United States, or an area that's got lots of geothermal features and lots of amazing things going on, spewing water and steam out of this hole in the ground. It's been heated by volcanic material that's relatively close to the surface. And of course, again, it's a very different phenomenon, but I thought there was an interesting correspondence there where the steam is escaping through this narrow opening in the ground, and on the left, the star is emitting this material through this constriction in this disk of matter close to the star. And so again, very different physical phenomena, very different physical scales, but again, just this idea that we're seeing this continuum of nature and natural phenomena from the micro to the macro. And finally, sort of one of my favorite comparisons, again, we see this galaxy, Barred Spiral Galaxy, and you see 1300 a galaxy, as we might see our own Milky Way galaxy if we could fly very far away from it and look back towards home. And if we could see our whole galaxy, this is kind of what it would look like. But on the right, we see a real image of our Milky Way galaxy from the inside. So this is the Milky Way that you can see at a dark site away from lights. This is a fairly long exposure, so we see it brighter than we would see it with our eyes, but this is a very dark site in Utah in the United States. And but again, I love this correspondence where we can see it's a different galaxy. It's our Milky Way versus this very distant NGC 1300, but we're seeing a galaxy on the right. We're seeing it from the inside, but we're still seeing the stars and the gas and the dust lanes and the same features we're seeing from the outside in this distant galaxy. So I just love that correspondence. So finally, I've been talking a lot about the past. So there's a lot of history with Hubble. It's again been active and producing groundbreaking science and beautiful images for 32 years. And it still has a long way to go, we hope. Everything, as far as I understand, is still working pretty well, but it won't last forever, unfortunately. But NASA is always looking to the future, and now there's this new telescope around. It's called the James Webb Space Telescope. It was launched back in December and has now pretty much been fully deployed. It was a very complex process, a very complex machine, probably the most complex spacecraft that's ever been launched, and certainly the most complex astronomical observatory. And it will do groundbreaking science, just like Hubble has. It will do different groundbreaking science because it's primarily, it is entirely sensitive to the infrared and not visible light as we can see. So it will do very different science, but follow on to a lot of the kinds of science that Hubble has been doing. So where Hubble has been able to look very, very deep into the universe, the background image is one of the deep fields that Hubble has taken, looking at a very small piece of the sky, but for a very long time, so it can image very, very, very faint objects. But Hubble has a limit because of the limits of the wavelengths that it can detect. Because of the expansion of the universe, the light is shifted. Very distant objects are moving away from us. The farther away they are, the faster they're moving, and therefore the light is shifted much more towards the red. And at the very distant reaches of the universe, that light is shifted completely into the infrared part of the spectrum where we can't see it and Hubble's instruments can't detect it. So that's the primary reason for building the James Webb Space Telescope, which will be sensitive to the infrared light. So it's been an amazing ride to see this development. And in fact, one of the neatest things was to see was when they deployed it, there was a camera on the launch vehicle, and as they let it go, there's live video of the deployment of the telescope, and we can see the Earth in the background, and Webb is getting farther away, and ultimately, the only part of the deployment really that we can see before it disappeared is the deployment of one of the solar panel. But this was a kind of an unprecedented view of the deployment of a spacecraft, and very exciting to see after so many years of development of this mission. So just as Hubble has been in development for so many years and in operation for so many years, James Webb will continue on to do that. And just watch for the next. It's getting close to being fully deployed and calibrated. There's still some work to do. There goes the solar panel getting deployed. But the last I heard, just in the last few days, all the instruments are now in focus, and remaining work is to complete the calibration of the instruments, and that will take place in the next few weeks to months, and we will start seeing science data, hopefully, in the next month or so, probably. June, I think, is on the schedule. So this is one of the images that they use to demonstrate that all the mirrors, now this is composed of multiple mirrors that all have to be in phase, all have to be in focus together, all pointing in the same direction. And this image of a fairly bright star demonstrated that all the images were together, working together. And yet you can see in this fairly, not even very deep image, that you can see lots and lots of galaxies in the background. So that's one of the things that Webb will be looking at. So stay tuned. And finally, I just want to give a little ad for if you want more information, all these images and more are available at hubblesite.org, and much other stuff, much other content. So this little video is an example of the kinds of things that the office I worked in, the Office of Public Outreach at the Space Telescope Science Institute. This is a visualization, a three-dimensional visualization of a nebula and cluster. We don't have actual depth information, 3D information. We don't have 3D images, but with some informed guesses and a lot of science background and a lot of sophisticated software, folks are able to produce this wonderful fly-through of this region of space to, mostly to demonstrate that space is not just two-dimensional as it appears in these images, these two-dimensional images, but there's a great deal of depth in space, not just from the closest things that we can see in our solar system to the very distant, most distant places in the universe, these very distant galaxies, but within these regions of space, it's also three-dimensional. So these clusters have depth. These clusters are roughly globular, and then all these nebular features have depth and structure. And so these 3D fly-throughs give you a little taste of that. And so I hope that's given you a good perspective on what Hubble has accomplished and a little bit of background on where these images come from and what it takes to produce them. And I thank you for your attention.
Thank you so much, Zolt, for enlightening us on about how the process of the creation of these wonderful and beautiful images are done. And it has elicited a lot, not a few questions from our audience. And I would like to go now to our Q&A portion where I will reading some of these questions. And I guess this is related. You answered this partially already from Joseph Gutierrez. The question is, as the James Webb Space Telescope is being put into use, what is the future for the Hubble Space Telescope? Will the James Webb Space Telescope complement the data from the Hubble Space Telescope?
Absolutely, they're very complementary. So as I said, Webb will be working in the infrared, whereas Hubble is primarily in the visible part of the spectrum. So they're looking at very different phenomena in the universe. But working together, you'll get even more information out than either one separately. So this happens all the time with multiple observatories. So Hubble is not working alone. Hubble is working together with all the other observatories in the world. And each observatory has its strengths. So astronomers can use different instruments to study different aspects of the things they're studying. So Webb will certainly Hubble will complement what Webb is doing. And that was one of the goals, to have Hubble still operating while Webb was working. And the fear was, while there was numerous delays in the launch of Webb, and the fear was that Hubble would not be here anymore while Webb was working. But fortunately, Hubble is still working, Webb is now launched, and there's great promise there.
Thank you. So another question. How does the coordination go between the principal researchers and you as regards to what they need or their scientific objectives?
I will say that we worked very closely with the scientists, and that was one of the most rewarding parts of my job, is working with these scientists, some of whom I'd known about for many years studying astronomy, and there are many other new people that I met, wonderful people to work with. So, there's kind of two aspects. One was, again, that we were producing images that illustrated the science content. And so in that case, we worked very closely with the astronomers to produce images that did, show what they wanted to show. One example is, it's an image that I did not show, but there's an image from the Hubble telescope of the Great Orion Nebula, which is a very large, bright region where stars are forming. And the reason that astronomers took the image was to study the fainter stars and protostars, the brown dwarfs and red dwarfs in the region. So we wanted to produce an image that showed those objects and showed them as red objects. So it was a bit of a challenge to work with the data as we had it, but I think we ended up with not only a spectacular image, but an image that did illustrate what the scientists wanted to show. So in other cases, we had the good fortune to have a little bit of time on the telescope to produce images that were made primarily to produce an attractive image. Although being Hubble data, it was always useful for science, whether it was taken primarily as a demonstration image or taken purely for science. But yeah, we did work very closely with the scientists, and not only the images, it was the text and the illustrations and the graphics that were produced in the office I worked in by some very talented people, writers who produced text that explained very succinctly but completely. And they worked very closly with the scientists to craft a story that wasn't dumbed down too much, that was accessible to many people, and at least accessible to reporters for news organizations that would then write the stories for their audience. And so it was very much a team effort between the people in the office and the scientists to produce these results.
Thank you. There are some image processing questions here. For example, the next question is, there is some art to processing images, and the images are captured via filters. How do you decide on what the color balance is to images, given how it looks visually, versus enhancing features? Is that clear?
Yes.
How do you decide on what the color balance is to images?
It can be a challenge depending on the data. I had sort of a few goals in mind when I was doing this. And one was to visualize as much of the information inherent in the data as possible. That is, for example, in the image of the galaxy that I showed, where we saw the very center, details in the very center of the galaxy, I always wanted to preserve details like that I knew was in the data. And yet the challenge came in where you have this enormous dynamic range. So from the faintest parts of the image, you wanted to show details that might be very close to the noise. That people that do this sort of image processing are very familiar with noise in these images, and yet preserve the brightest part, the details in the brightest parts. So the color balance in some cases was relatively straightforward with the broadband filters. It's fairly easy. It's closer to our visual perception. So, you kind of know what's supposed to be red, as I described before. You kind of know what's supposed to be blue, and you sort of adjust the balance in that way. With the narrowband filters, it's a little bit trickier. But again, I wanted to have a range of kind of make use of and visualize the full range of colors and the full range of tonalities. That is the gray levels in the image. That's kind of something I learned on my photography side, is to make use of the full dynamic range that's available in however you're presenting your image, whether it's in print or on a screen. So those kind of guiding principles always was in the back of my mind.
Thank you, Zolt. Another question, but this time in relation to the James Webb Space Telescope and images. From Joel Goodman. Will James Webb Space Telescope process images by capturing 3 different infrared wavelengths and assigning them to RGB channels? How do astronomers decide which IR wavelengths to view in, like O3, etc.?
Yes, Webb will produce images very similarly to the way Hubble produces images. They'll have multiple filters in the cameras, so they will be able to produce color images. And in general, I think the paradigm is the same, that they will primarily assign the colors in wavelength order. So the shortest wavelengths will be assigned to blue. The longest wavelengths will be assigned to red. And since we can't see infrared light and we don't know, we have no color concept of infrared colors, we will translate those colors into the visible colors, just as we translate the colors with visible light. So it will operate, the technology will be the same. The results may be a little bit different. And you can actually get a pretty good idea of what some of those images will look like by looking at, there already are examples. So the Spitzer Space Telescope is a orbiting observatory that NASA launched years ago that operated in the infrared. So in a very similar regime to what Webb will be doing, the big difference is that Webb has a much larger mirror, so it can gather much more light and the resolution will be much better. So, but if you want to get a sort of qualitative feel for what the Webb's images will look like, look at Spitzer's images and the kinds of science that Webb will be doing is similar to the kinds of science that Spitzer has done. Although not so much in a very deep universe, Webb is really designed partly to look at the very deep universe. But as far as the images are concerned, Spitzer is a good example. And so Webb is more of a follow-on to Spitzer than it is to Hubble. But yes, there will be images, there will be color images, and it will be interesting to see those comparisons between what Webb can do and what Spitzer did and what Hubble has done.
Yeah, and here's another related question and comment from G-Man. Thank you, Zolt. That was great. You mentioned additional infrared capabilities on James Webb Space Telescope. What other lessons learned from Hubble were applied to James Webb Space Telescope? So what other lessons learned from Hubble were applied to James Webb Space Telescope?
That's an interesting question. I think I'm not that, I mean, I sort of have heard second and third hand about the development of Webb. So, you know, I'm not very experienced with that, but I think in general, many of the lessons probably have more to do with operating the observatory and things like data archiving, even things like that. You know, how do you do proposal submission and things like that? The technology, I think, there's a lot of new technology on Webb, partly because it's in the infrared, partly because it's not serviceable. It's 1 million miles away. So it's a different spacecraft regime, sort of. And yet, I think, again, the operation and the development experience that went into Hubble certainly has fed in to the development of Webb. And I'm hoping one of the lessons they learned was, and I know one of the lessons they learned was testing. Because as you know, I'm sure, there was a major flaw in Hubble. The mirror is not what it should have been. And so there was an optical aberration in Hubble's mirror. Fortunately, it was able to be characterized very precisely, and so they could design optics to correct for that aberration. So, but that happened because there was an error in a test procedure. And so I think one of the lessons that was learned was to be very aware of the testing and how the testing happens. And I know that there was multiple tests going on with Webb. There were some interesting things. I mean, they had to, I mean, there's this huge machine, right? And they had to be able to test it in a vacuum. So there's this vacuum chamber at Johnson Space Center that they sent the telescope to, and it turns out it was originally designed for the Apollo missions back in the 60s and 70s, and it was sort of mothballed for a while, and they resurrected it and made it usable for the Webb telescope. So there was an enormous amount of testing that went on.
Thank you. Let us leave the James Webb Telescope for now, and this question is more for the astronomical community. The question is, what pioneering techniques did you in the Hubble Imaging and Scientific Visualization team use that are now benefiting the astronomical community?
Well, I guess, I mean, most of the techniques that we used were not really new. people have been making color pictures from astronomy data as long as color photography, color technology has been available. The difference today is that it's much more convenient with digital technology than it was in the photography days. I mean, David Malin was the premier color astrophotographer in the photography days. And he used large telescopes. He took glass plates in different filters and combined those in the darkroom to produce color prints and color images. So the techniques, the basic paradigm is not really new. But I think the newness, I think the part of the newness is, again, the convenience of the technology, the prevalence of the technology, and with Hubble, one of the things that made Hubble kind of so widespread in people's, in the media and in the public in general, was really the rise of the dissemination of the information. So the rise of the internet and the World Wide Web, along with very concurrent time scale with Hubble, so that the results from Hubble got disseminated extremely widely compared to earlier observatories. So, you know, because there was so much more information coming out, and NASA actually has a mandate to distribute this information, and then it became more convenient to distribute it. So it became more, people became more aware of it. But the techniques, so I think the techniques are such that, I mean, this idea, as I showed in the 3-color image of the Eagle Nebula, using narrowband filters and combining them in that color method, putting the hydrogen in the green rather than the red, was something that was fairly new. I didn't come up with that. That had been done before. But again, it became more, people became more aware of it. And I only learned later, much later, after those images started coming out, the people in the amateur community, the backyard astronomers, were calling that the Hubble palette. And we never referred to it that way. It was just the way you did it. So that was one interesting thing. So that became widespread in the astrophotography community. So that's the kind of thing.
Thank you so much for explaining how the term Hubble palette came into being. There's another question is, how long really does it take you to finish processing all of these images, like the mosaics and, for example, the pillars of creation?
How long?
How long does it take you to process them?
It varies a lot. You can put an image together in a few minutes, but then, you know, other ones like you mentioned mosaic, so that takes a lot longer, and it's a little easier now. There's a lot more sophisticated software, but 20 years ago it was a little bit more manual. I used a lot of Photoshop techniques to stitch images together more manually, and so that was very time consuming. The Karina Nebula image, for example, took a lot of time, and because that was a combination of very different images, images from Hubble and images from the ground, that was very, very time intensive. I guess maybe that's why it's one of my favorite images, because I devoted a lot of time to it. But so it varied a lot. You know, as anybody that produces images even from a backyard telescope knows, it can be very time consuming, but given a little bit of experience and you know, data that's more cooperative, it can be fairly quick. Maybe not a satisfying answer, but all over the place. What can I say?
I think we're down to the last 2 or 3 questions, but this one is a fairly long question, but I think you answered it already in some partly, but I would like to read it anyway. So the question is, The Hubble Space Telescope can see from visible light to some infrared and ultraviolet, while the James Webb Space Telescope is primarily optimized for the infrared. What would be the biggest difference what the public would see from the Webb images compared to Hubble? What would be the biggest difference between them, the James Webb images compared to the Hubble?
I think I think the biggest difference will be in images like the Horsehead Nebula image that we saw, where if you compare that infrared image with a visible light image, it's almost a negative. So what's light in the visible is dark in the infrared and vice versa. So it's regions of space like that where the visible light is blocked and the infrared light comes through, where you'll see the biggest difference. And looking at any one image, it may not be obvious that it's an infrared image, but if you compare it with the visible, it will be very different. And the colors will be different because the physical processes are different. And then, again, in the very distant universe, it's more subtle, but we'll be able to see farther. So, or image objects that are farther. And again, it probably won't be that much of a difference, but scientifically and technically, it will be a dramatic difference. So I don't know if that answers the question. The other area I think is in the solar system, and things look very different in the infrared in the solar system. And there was surprisingly, you think of Webb as being optimized for the very distant universe, but there's a lot of science that will be done in the solar system, in the atmospheres of the gas giant planets, for example. There'll be a lot of science there, and also and this is more. And the other thing you have to remember is that a lot of the science, especially with Webb, will be done with spectroscopy, and that's the case with Hubble too. So it's not just the imaging, but much of the science is done through spectroscopy, and it's not as visually accessible to most people, but a lot of the science results that you hear about from Hubble and that you will hear about from Webb are done through spectroscopy, and that's where the big differences will be. So Webb will be able to study things like the atmospheres of planets around other stars. And the hope is that they can characterize those atmospheres to be able to determine whether they're suitable for life, for example. And that's something that only Webb will be able to do. And again, it won't be an imaging result. You won't see an image of a planet with clouds around whatever star out there. But they will be very dramatic results, nevertheless.
Thank you. This question just came in from Donald Thompson. Remark and a question. Zolt, great talk. When preparing a Hubble image for public release, you spoke of adjusting the colors to create a more dynamic image. How much of this was your own aesthetic taste, and how much was a straightforward application of existing principles?
Well, I'd have to say it's a combination, and I don't know the ratio of that combination, but there's no algorithmic sort of application there. This was done as a photographer would apply adjustments to a raw image, for example, coming out of the camera, and the same kinds of adjustments. So you have contrast adjustments, you have global contrast adjustments over the whole image, you have local contrast adjustments to adjust the dynamic range between brighter parts of the image and darker parts of the image. You can apply color adjustments globally or locally. I tended to stick with more global adjustments just to avoid the introduction of anything to the image that wasn't in the data. That was another guiding principle, to avoid introducing artifacts that I couldn't see in the original data. But otherwise, it was more or less a subjective application of, again, the same kinds of things that a photographer would use to make the image more appealing, more aesthetically appealing, and maybe more dramatic.
Thank you. This is again another recent question in the Q&A, but I really could not understand it. Maybe I'll just read it. In what form is sensor data when it is taken by whatever software puts on, in quotes, black and white? Additionally, did you ever personally have to create software yourself in resolving issues in data visualization?
Well, the answer to the second question is easier. No, I didn't really, well, I started out life on the Hubble project developing software. So we were developing the analysis software that scientists were going to use to analyze Hubble data. So in a sense, I did develop some of that. So it was more, in my case, it was the display and graphics part of that software. So, but it wasn't really developing software to do image processing per se. If I understand the question, the format of the data that we have to work with is FITS. So that's the standard astronomical data format. It's been in the astronomical community for many decades and is used by all observatories now. So that comes out of the Hubble Data Archive. You get FITS data, and the analysis software understands FITS data. Now, standard image processing software doesn't understand FITS data. So there has to be an intermediary, like Photoshop natively doesn't understand FITS data. So for many years, for some time I used a processing package called IDL, which a lot of astronomers have used that did work with FITS data, and we produced TIFF images that could then be read by Photoshop. And then later on, this piece of software was developed. I had some hand in developing this called FITS Liberator. It was primarily motivated by the European Space Agency, the Hubble office of the European Space Agency, but working with several people, developed this software to just read and display the FITS data and be able to scale it and create files that then Photoshop could understand, or other image processing software could understand. And so that's what primarily I used. Now there's a lot of other software out there that backyard astronomers now are using. Like the gold standard, I suppose, is PixInsight, that does work with FITS data and has a lot of very sophisticated procedures to work with that data, to both calibrate data out of a camera and display and scale the data and produce color images. There's other ones, there's other software that does that now. So it's a little bit easier today. I mean, the software is not easy to use. There's a substantial learning curve, but I'm still learning. But so I don't know if that, I hope that answers the question.
Thank you, Zolt. But I'll just like to throw in a question coming from myself. I noticed that you're also a backyard astro imager. I noticed that when I was looking at your biography. So how do you differ from the usual backyard amateur astrophotographer? Because in our audience, I believe there are a lot of amateur astrophotographers there. So what makes you different from them? Because you had all of this experience with the Hubble, and now you're doing backyard astro imaging.
I don't think I'm that much different. In fact, I often marvel at the equipment that some people have. I mean, the equipment is a big limiting factor, and location. So I don't have the optimal location. I also marvel at people that have, that live in very dark sites and have fabulous equipment. I have some good equipment, but it's not the best equipment. It's not the state of the art.
I'm happy to see you're using the same equipment that we're using.
It's off the shelf equipment. I don't think I'm really that different. Maybe just in the processing, I come more from the science side, and so again, with the images that I produce, I have the same mindset. So I'm trying to produce images that are true to the data, that reflect what I think the objects that I'm looking at should look like. And so, many amateurs may come from the equipment side, they get interested in it because of that, and that's great, but they may not be as experienced with the science and the content of the objects. So that may be one difference, but there's a lot of amateurs who are very experienced with the science side of it. But I don't think I'm really that different. In fact, again, I have, a lot of people have much more experience than I do.
Thank you. But you really inspire us as well. We amateur astrophotographers. Before I don't like to go. I think this is the last question, and it's a sort of I would call this a Miss Universe question. What do you think is Hubble's greatest and most enduring legacy to humanity?
Well, for humanity, I really think that it's this combination of the groundbreaking science that Hubble's been able to do, looking at the entire scale of the universe, again, from our near neighborhood planets, and learning more about the planets to the very, very distant edges of the universe. And yes, other telescopes do that, but the other thing about Hubble is the vast penetration of this knowledge that's been in the public. And again, I think that's happened because of the concurrence of the internet, the development of the internet. And so, Hubble is familiar to more people than any other astronomical observatory, regardless of whether there's lots of observatories that merit that kind of attention, but Hubble, for all these reasons, has gotten into the public's awareness, and so I think that's furthered the appreciation of what the science that Hubble has done. So I think it's all those things together, the deep science and the understand. One of the things that I often reflect on is that science often happens in a way that brings more questions than questions and answers, and Hubble has certainly done that. So, for example, just one small example, Hubble started looking at planetary nebulae. I showed one example of a planetary nebula. And people, I think, before that thought, planetaries are all kind of the same. But every planetary nebula that Hubble looked at was different in a different way. And being able to see them in more detail, study them in more detail, gave us this awareness of the richness of the differences and the depth of information that you can have about things, and that is accessible to you now. So that's one of the things I think that Hubble has contributed to.
Thank you so much. thank you for answering all of those questions. There are a lot of them. That shows you how much the audience really appreciated and understood your talk, and that elicited a lot of these questions. I would like now to take this opportunity, Zolt, to give you a small token of our appreciation. This is a certificate of appreciation from the Astronomical League of the Philippines. And this certificate is presented to Zolt Levay for his invaluable insights, experiences, and expertise shared with the participants of the webinar entitled Visualizing Hubble's Colorful Universe, held during the 2022 Global Astronomy Month, given this 30th of April, 2022, signed by the President, Mr. James Kevin T., and the Vice President, Dr. Jose Francisco Aguilar. Thank you so much, Zolt.
Well, thank you very much. It's been an honor and a privilege. And thanks again for everyone for inviting me. And it's a great audience, some really great questions, and it was my pleasure.
Thank you.
Okay, thank you, Zolt.
Zolt, personally, we want to thank you. That was an awesome presentation and awesome images you and Hubble perfect pair.
Thank you.
Thank you. Thank you again, Imelda.
Thank you. So we will now have a short 7-minute video presentation on the highlights of Philippine astronomy and the Astronomical League of the Philippines.
Chat, group chat. You might call that.
Before or after the video? Okay, let's have a group chat first with Zolt. Is that okay, Zolt?
Yes.
Yeah, let's have a group chat.
Casey.
Yeah, I'll take the photo. So 3, 2, 1, say cheese. Hold on. Let me check. Okay, I'll take another one. 3, 2, 1. All right.
Okay, this is now traditional for Zoom webinars. We take group pictures after. Thank you so much. I'll share my screen again for the video presentation. So this is our video presentation done by June and by Casey. Thank you again, Zolt, for very nice lecture today. And before we end, I would like to announce our succeeding lectures for the next weeks. Next week we will be having the third astronomy expert series speaker, Mr. Joe Rayo, who will talk about the Night of the Shooting Stars on May 7, 2022 at 8:30 p.m. Philippine Standard Time or 12:30 UTC. And on May 29, 2022, we will have a talk by Mr. Fred Espinac, Mr. Eclipse himself, who will be talking about predicting and chasing solar eclipses. Kindly view our website at https://astroleaguefields.org for more details about these talks and how to register. Registration is free. Thank you so much. So that ends our webinar.
So we're offline now, Jeff?
No, not yet. So I'm gonna end the webinar now, and we can meet in a Zoom meeting. Give me about 5 minutes to.
Yeah.
Thank you very
Zolt.
much, Zolt.
Thank you,
Zolt,
Zolt,
thank you.
for
Thank you so much, Zolt.
giving us a good lecture.
Enjoyed it.
Thanks, Zolt.
We
Thank you,
enjoyed
Zolt.
it. Thank you so much. Take
Yep.
care.
Bye.
Thanks for our
Bye-bye.
participants as well. Thank you.
Thank you. Thank you for all the participants. See you
Yes.
next week.
Hope you can join us again.
Yeah, please. Thank you.
Thank you very much.
Bye-bye.
Bye.
Bye.
Bye.